Hi everyone, welcome to this series of supply chain lectures. I am Johannes Vermorel, and today I will be presenting my fourth lectures, Programming Paradigms for Supply Chain. So when I am being asked, Mr. Vermorel, what do you think is the areas that are of most interest to you in terms of supply chain knowledge? One of my top answers is usually programming paradigms. And then, not too frequently, but frequently enough, the reaction of my audience or the person I'm talking to is programming paradigms, Mr. Vermorel, what the hell are you even talking about? How is it even remotely relevant to the task at hand? And here, and those sort of reactions, obviously they are not so frequent, but when they happen, they invariably remind me of this completely incredible quote of Robert Heinlein. So Heinlein is literally considered as the dean of supply chain writers. It was the man who, during the 20th century, really turned science fiction into something that is taught at university as real literature, while before it was just like a popular subgenre that was not worthy of actual academic interest. And he has this fantastic quote that I'm going to read on the competent man. What is competence? A human being should be able to change a diaper, to plan an invasion, to butcher a hog, to con a ship, to design a building, to write a sonnet, to balance accounts, to build a wall, to set a bone, to comfort the dying, to take orders, to give orders, to cooperate, act alone, solve equations, analyze a new problem, pitch manure, program a computer, cook a tasty meal, fight efficiently, die gallantly. Specialization is for insects. The emphasis is mine. And yet, so competency is an incredibly multifaceted problem, and especially in supply chain where we have wicked problems on our hands. Those problems, they don't have, they are almost as challenging as life itself. They don't have any, I would say, I believe that it's really worth your time, and it could bring a lot of value for your supply chain. It's those very idea of programming paradigms. So the story so far, this is the fourth lecture. In the first lecture, we have seen that, in essence, supply chain problems are wicked. So anybody who is talking of optimal solutions, of that I have is basically missing the point. There is nothing that is even remotely close to optimality. You can have adversarial behaviors that just undo what you've just done. So we have to cope with supply chain, which requires a very specific perspective. And then in the second lecture, where I outline the quantitative supply chain, it's a vision, and I'm listing 5 key requirements that I believe to be requirements for greatness. You don't need them if you want to be an average or below average supply chain. By definition, half of the supply chains are below average supply chains. But if you want to achieve greatness, I believe that those 5 elements that I've listed in the second lectures are required. They are not sufficient, so it's just a set of requirements on their own. They will not do the magic, do the trick, but I don't think that you can bypass any of those elements. And then in the third lecture, where I discuss about product delivery, and I mean software product delivery, I defended the proposition that supply chain optimization requires software products to be addressed properly in a capitalistic fashion, but you cannot find such a product on the shelf. It's just not possible. There is too much diversity, too much. This is way beyond the technologies that we have at present time. So it's going to be, by necessity, something completely bespoke. And thus, if it is a software product that is going to be bespoke for the company of the supply chain of interest, then there is a question of what are the proper tools to actually deliver this product. And that brings me to the topic of today. Well, the proper tools starts with the right programming paradigms, because we are going to have to program this product one way or another. So the story so far was we require programmatic capabilities to deal with the optimization side of the problem, by the way, not to be confused with the management side, the optimization side. And what we have seen, that was the topic of my previous lecture, is that Microsoft Excel won so far, from very small companies to very large companies. It's ubiquitous, it's used everywhere, and I would argue that even in companies that have invested millions of dollars in super smart systems, Excel still rules. And why? Because it has the right programming properties. It's very expressive, it is agile, it's accessible. When I mean accessible, I mean it's accessible to people who are not software engineers. This is an absolutely crucial property. If your programmable stack, whatever you're using, is only accessible to software engineers, the whole thing will devolve in the fact that supply chain practitioners will resurrect Excel sheets and move on and ignore whatever tooling you've put in place. And then it's maintainable, and we can get more on that. And yet, Microsoft spreadsheets won, but they are not the end game. They are not. I firmly believe that you can do so much more, but we need to have the right tools, the right mindset, the right insights, the right programming paradigms. So let's proceed. Programming paradigms might feel something that is overly obscure to the audience, but it's actually a field of studies that has been super intensively studied during literally the last 5 decades. And there has been like an immense amount of work done in this field of study. It's not, I would say, widely known to a wider audience, but it is something where there are literally entire libraries filled of exceedingly, I would say, high quality work that has been done by a lot of people. So today, I am going to introduce, a series of 7 paradigms that I personally invented, or Lokad did not invent any of those ideas. We stole them from people that were mostly that invented them before us, and all those paradigms have been implemented and have been, I would say, in Lokad, the software product that we are having, and they have been, after nearly a decade of running Lokad in production, running supply chain in production, leveraging those paradigms. I believe some of those paradigms have been introduced in Lokad more recently than others, but they have been absolutely critical to the operational success that we have enjoyed so far. And so, let's proceed through this list with static analysis. So what is the problem here? The problem, in essence, is complexity. So how do you deal with complexity? In supply chain, you are going to face enterprise systems that have hundreds of tables. Each table has dozens of fields. If you're considering a problem that is as simple as inventory replenishment in a warehouse, you have so many things to take into account. You can have MOQs, you can have price breaks, you can have forecasts of the demand, forecasts of the lead times, forecasts of the returns. You can have shelf spaces that limits what you can do. You can have reception, capacity limits. You can have expiration dates that just make some of your batches obsolete, etc. So you end up with tons of things. And now the question is, in supply chain, the idea of move fast and break things, it's just not the right mindset. If you order inadvertently, for $1 million worth of merchandise that you don't need at all, this is a very, very costly mistake. So you can't just say, oh, we are going to have a piece of software that drives our supply chain, just takes routine decisions, and literally, when there is a bug, things cost millions. No, we need to have something that has a very, very high degree of correctness by design. We do not want to discover the bugs in production. And again, this is very different from your average software. If you have a crash, no big deal, you have a problem, you just restart the machine, restart the thing, etc. When it comes to supply chain optimization, this is not your usual problem, your usual game. You can't just, if you just passed a massive order, which is completely incorrect, to a supplier, you can't just phone your supplier 1 week, 1 week later to say, oh, my mistake. No, forget about that. We never ordered that. I'm very sorry. I mean, those mistakes are going to cost a lot of money. So static analysis is, it has this name because the idea is that it is about analyzing a program without running it. So the idea is that you have a program that is written with statements, keywords and everything. And the question is, without even executing this program, can you already tell if the program exhibits, problems that would be, almost certainly negatively impacting your production, especially your supply chain production? And the answer is yes. These sort of techniques do exist, and they are actually implemented, and they are exceedingly valuable. So just to give an example here, so here on the screen you can see an Envision screenshot. So Envision is a domain-specific programming language that has been engineered for almost a decade by Lokad that is dedicated to the predictive optimization of supply chain. And what you are seeing is a screenshot, literally a screenshot of the code editor of Envision that is running, that is a web app. So it's just a screenshot of a small piece of a web app. And it's literally what you can use online to edit code, Envision codes. And as you can see, the syntax is not widely different from Python. It was heavily inspired by Python. Influenced, I would say, by Python. And what is the thing that I'm illustrating in this tiny screenshot where there is 4 lines? I'm illustrating the idea that if you're writing, I'm going back to this inventory replenishment in a warehouse problem. You're writing, you have a big piece of logic that is maybe going to be, unlike this example that I'm giving, that is 1,000 lines long, and you introduce, at some point, some variables, some economic variables, for example, of interest, price breaks, and through a logical analysis of the program, you see that those price breaks have no relationship whatsoever with the end results that end up being returned by the program, which are the quantities to be replenished. So here, you have obviously a problem. You have introduced an important variable, price breaks, and those price breaks, they are logically having no, they can't even influence the end results. So here we have a problem that it's obviously something that we can detect through static analysis, and it's something that is an obvious problem, because if we introduce variables, and those variables in the code don't have any impact on any of the output of the program, then they serve no purpose at all. So then we are faced with 2 options. Either those variables are actually dead code, and then the program should literally not compile. You should just get rid of this dead code just to reduce complexity and not pile up accidental complexity. Or that was a genuine mistake, and actually there is an important economic variable that should have been plugged into your calculation, but you just dropped the ball just because you were distracted or whatever. So static analysis is absolutely fundamental to achieve any degree, I believe, of correctness by design. And again, it's about fixing things at compile time. So when you write the code, compile, even before you touch the data, because if problems emerge when you run them, chances are that your problems will only happen, during the night, when you have the nightly batch that is driving, the warehouse replenishment. I mean, the program is likely to run at odd hours where you have nobody attending the program. So you don't want something that crash while there is nobody, in front of the program. It should crash at the time when where people are actually writing the code. Now, static analysis has many purposes. For example, at Lokad, we are also using static analysis for the WYSIWYG edition of the dashboard. So WYSIWYG is what you see is what you get. So imagine you're building a dashboard, just for reporting for humans. So the dashboards has line charts, bar charts, tables. They have some sort of colors, all sort of styling effects. And you want to be able to do that visually. You don't want, to tweak through the code, the style of your dashboard, because it's very, very cumbersome. So you want to be able to do it visually, and yet all the settings that you've just, implemented, they are going to be re-injected in the code itself. And that is done through static analysis. Another thing at Lokad, which is maybe not so of such an importance for supply chain, I would say overall, but certainly for Lokad, for our undertaking, it was of critical importance, was we are dealing here with a programming language that we are engineering. And obviously, this is a piece of a language called Envision. And when we started, we knew from day one that mistakes were going to be made. We didn't have, some kind of crystal ball to just have the perfect vision from day one. So we knew from day one, almost a decade ago, that mistakes were going to be made. And the question was, how can we make sure that we can fix those design mistakes in the programming language itself as conveniently as possible? And here, Python was for me a warning tale, because Python, which is not a new language, Python was basically first released in 1991, so almost 30 years ago. And the migration from Python 2 to Python 3 took to the entire community almost a decade. And it was a nightmarish process, very, very painful for the companies involved in this migration. And so my perception was the language itself did not have enough construct. It was not designed in a way that you could migrate programs from one version of the programming language to another version of the programming language. It was actually exceedingly difficult to do so in a completely automated manner. And why? It's because Python has not been engineered with static analysis in mind. So you really want to have, when you have a programming language, you really need to have, for supply chain, you really want to have a programming language that have excellent quality in terms of static analysis, because your programs will be long-lived, and supply chains don't have the luxury to say, hold on, for 3 months, we are just rewriting the code, wait for us, the cavalry is coming, it's just going to be not working for a couple of months. It's literally akin to fix a train while the train is running on the track, is on the tracks at full speed, and you want to fix the engine while the train is working. That's what it looks like, fixing supply chain stuff that is actually in production. You don't have the luxury to just pause the system. It never pauses. Okay, second idea, second paradigms, array programming. So again, we want to have complexity under control. That's a big recurring theme in supply chains. And here, we want to have logic where we don't have certain classes of programming errors. For example, whenever you have loops or branches that are written by explicitly as such by programmers, you expose yourself to entire classes of very difficult problems. For example, it becomes exceedingly hard when people can just write loops, arbitrary loops, to have guarantees on the duration of the calculation. And you would say, well, it looks like a super niche problem, and I would say not quite. If you want to run a supply chain optimization, just look at how things are going to work in practice. It's going to be at midnight. Let's say you have, I don't know, a retail chain of some kind. At midnight, they will have completely consolidated all the sales from all the entire network. And then the data will be consolidated, passed to some kind of other system for the optimization itself. And then this system will have exactly a 60-minute window to do the forecasting, do the inventory optimization, do the the decision of the reallocation for what are the replenishment for every single store of the network, and then once it's done, it's going to pass the results to the warehouse management system so that they can start preparing all the shipments and the trucks are going, the teams are going to start loading the trucks, maybe at 5 a.m. in the morning, and then by 9 a.m. the stores are opening with having already received and put on the shelves the merchandise. But you see, you have a very strict timing, and if your calculation, goes outside of this 60 minutes window, you're putting at jeopardy the entire supply chain, entire execution of the supply chain. So you don't want something where you're just going to discover in production how much time things takes. So if you have like loops where people can decide how many iterations they are going to have, it's very, very difficult to have any proof of the duration of your calculation. And bear in mind that this is supply chain optimization we are talking about. You don't have the luxury to do peer review, and double check everything. Sometimes, for example, in the present period where due to the pandemic, some countries are shutting down, some others are reopening, quite erratically, usually with a 24 hours notice. You need to react to be super swift. So array programming is the idea that you can operate directly on arrays. So if we look at the snippet of code that we have here. So again, this is InVision code, so the DSL of Lokad. And to understand what's going on, you have to understand that when I write orders.amount, what comes, so orders.amount is a variable, and the orders is actually a table in the sense of relational table, as in a table in your database. And for example, here in the first line, amount would be a column in the table. And so on the line 1, what I'm doing is that I'm literally saying for every single line of the orders table, I am just going to take the quantity, which is a column, and to multiply it by price, and then I get a third column that is dynamically generated, if you want, which is amount. By the way, the modern term for array programming nowadays, it's also known as, data frame programming. But the actual, the field of study is quite ancient. It goes back, 3 or 4 decades in the past. Maybe 4 or 5 actually. And so it has been, the field of study has been known as array programming, even if nowadays people are usually more familiar with the idea of data frames. So line 2. What we are doing is that we are doing a filter, just like SQL, we are filtering the dates, and it just so happened that the orders table has a date, so it's going to be filtered, and it says date that is greater than today minus 365, so it's days. So we're saying we keep the data from last year, and then we are writing products sold last year equals sum of orders amount. So now the interesting thing is that we have what we call a natural join between products and orders. Why? Because every order line is associated to one product and one product only. And one product is associated to 0 or more order lines. So in this configuration, you can directly say, I want to compute something at the product level that is just a sum of whatever is happening at the orders level. And that's exactly what is being done at line 9. You might notice it's very, I would say, the syntax is very bare. You don't have many, lot of stuff that just are, I would say, accidental technicalities. I would pretend that this code is almost entirely devoid of any, of any accidentalities when it comes to data frame programming. And then the line 10, 11, and 12, we are just putting a table on display on our dashboard, which can be done, again, very, very conveniently, list of products and then 2 products. So the upside of, there are many, many upsides of array programming for supply chains. I mean, first, it eliminates entire classes of problems. You're not going to have like off by one bugs in your arrays. You don't have. It's going to be way easier to parallelize and even distribute the computation. And that's very, very interesting, because it means that you can write a program and have the program that is executed not on one local machine, but directly on a fleet of machines that lives in the cloud. And by the way, this is exactly what is being done at Lokad. And that is, this automatic prioritization is of I would say, super high interest. Because you see, the way it works is that when you do supply chain optimization, what are your typical consumption patterns in terms of computing hardware? It's super intermittent. If I go back to the example I was giving about the 60-minute window for the retail networks doing the store replenishment, it means that there is 1 hour per day where you need compute powers to do all of your calculation, but the rest of the time of the day, the other 23 hours, you don't need that. So what you want is a program that is, when you're about to run it, is going to spread on many, many machines, and then once it's done, it's just going to release all those machines, and then so that other calculation takes place. Because the alternative would say, if you have a very intensive calculation, would be you would need many, many machines. So you're renting many machines that you're paying all day long, but you're only using them, 5% of the time, which is very, very bad. So literally, this idea that you can distribute over many machines very rapidly, very predictably, and then surrender the processing power. First, it needs the clouds, it needs multi-tenants, it needs a series of other things on top that Lokad is doing. But first and foremost, it needs cooperation from the programming language itself. It's something that is just not feasible if you have a generic programming language like Python, because it's the language itself does not lend itself to this sort of very smart and relevant tricks. And that's more than tricks. It's literally about dividing your IT costs, hardware IT costs by 20, accelerating massively the execution, and eliminating entire classes of potential bugs in your supply chain. This is game changing. This is not a small thing. By the way, array programming already exists, in many aspects, such as, for example, that's why NumPy and pandas in Python are so popular for the I would say the data scientist segment of the audience. But the question that I have for you is, if it's so important and useful, why aren't those things not first-class citizen of the language itself? If it's literally all you do is channel through NumPy, then NumPy should be a first-class citizen. I would say you can do better than NumPy. NumPy is just about array programming, but on one machine. Why not do array programming on a fleet of machines? It's much more powerful and it's much more adequate when you have a cloud that is accessible. Hardware miscibility. So that's another tough one that is like super opaque and yet super critical. So what is going to be, the bottleneck? There is this saying that says that it's Goldratt that says basically that any improvement brought beside the bottleneck in supply chain is an illusion. And I very much agree with this statement. And so realistically, when we want to do supply chain optimization, what is going to be, our bottleneck? And my experience is it's going to be people, and more specifically, the supply chain scientists, who unfortunately for Lokad and my clients don't grow on trees. So your bottleneck are the supply chain scientists, the people who can craft the numerical recipes that factor in all the strategy of the company, that factors in all the adversarial behaviors of the competitors, and that really turns all this intelligence into something mechanical that can be executed at scale. Those people, what is the tragedy, I would say, of the naive way of doing data science? And when I started my PhD, I started a PhD 15 years ago that I never completed, by the way. So technically a PhD dropout. I quit my PhD to create Lokad. When I started my PhD, I could see that I stick around for a bit more than a year. Everybody in the lab was literally doing data science. So what most people were doing, they were writing code, obviously, for some kind of advanced machine learning model. They would press enter, And then they would start waiting. Why? Because if you have like a large data set, tenth of gigabytes, it's not going to be real time. So basically, the entire lab was people that were working, then they would write a few lines, then press enter, then go and grab a cup of coffee or read The Onion online or something, and thus productivity was exceedingly low. And my reaction when I went to create my own company, what was very high on my mind is I don't want to end up paying an army of super smart people that spend most of that day, sipping coffees, waiting for the damn program to complete so that they can have results and move on. And you could say, oh, but they just have to parallelize, many things at once and run, etc. Yeah, in theory, they could do that. In practice, I've never really seen that. Intellectually, when you're engaged, in finding a solution for a problem, you want to test your hypothesis, you need the result to move on. It's very, very hard to basically multitask on highly technical stuff and chase multiple, intellectual tracks at the same time. So, but there was a silver lining. There was a silver lining is that those data scientists, and now at Lokad supply chain scientists, when they do a bit of work, they don't end up writing 1,000 lines of code and say, please run. They end up writing usually like 2 lines. They add 2 lines to a script that is like 1,000 lines long, and they add 2 lines, and then they say, please run. And this script is running against the exact same data that they have just executed 2 minutes before, and it's almost exactly the same logic except for those 2 lines at the very, very end of the script, or maybe somewhere in the middle. But so literally, and maybe the script is processing terabytes of data. How can you process all those terabytes of data in seconds instead of tenths of minutes? Well, the answer is if for the former execution of the script, you've just recorded all the intermediate steps of the calculation. If you've recorded all the intermediate steps of the calculation, put them on storage, typically solid-state drives, those SSDs. They are very cheap, very fast, very convenient. The next step, you run your program. The system will just notice that it's almost the same script. It's going to do a diff. It's going to see that in terms of compute graph, it's almost identical except for a tiny few bits. In terms of data, it's usually 100% identical. Sometimes there is a tiny few things that have changed, but almost nothing. And so the system will auto-diagnose that you have only a tiny few things that you need to compute, and so you can have the results in seconds just because you realize that there is so little things that you actually need to compute to do this next run, and that can dramatically boost the productivity of your supply chain scientists. You can go from people who press enter and then 20 minutes they wait for the result to something where they press enter and 5 or 10 seconds later, bam, you have the result and you move on. So I'm talking of something that may seem super obscure, but in practice, we are talking of something that has a 10x impact on productivity. This is massive. And so what we are doing here is that we are doing a very clever trick that Lokad did not invent, obviously, which is we are going to substitute one raw computing resource, which is compute, for another, which is memory and storage. So you see, we have the fundamental computing resources, which are compute, memory, which is either volatile memory or persistent memory, and then bandwidth. So those are pretty much the fundamental compute resources. That's what you pay when you buy resources in a cloud computing platform, and you can actually substitute one resource for another. And the game is you want to have the biggest bang for your buck. So. And that's why, by the way, I'm just digressing a little bit. But that's why when people say, oh, you should be using in-memory computing, I would say nonsense, nonsense. If you say in-memory computing, it means that you're putting like a design on emphasis on one resource, but versus all the others. But no, it's literally something where you have trade-off. And again, the interesting thing is that you can have a programming language that makes those sort of things, a programming environment that makes this hardware miscibility, perspective paradigms way easier to implement. And usually, if you have a regular general purpose programming language, it is possible to do that, but you have to do it manually. And thus, it means that the person doing it has to be a professional software engineer. A supply chain scientist is not going to do this sort of shenanigans with the low-level, the foundational, resources, compute resources of your platform. So again, this has to be engineered at the level of the programming language itself. I'm not going to go too much into the details. Now, probabilistic programming. So that's very interesting because remember in the second lecture where I introduced the vision for the quantitative supply chain, my first requirement say we need to look at all the possible features. And a technical answer to this requirement is probabilistic forecasting. So you want to have to deal with futures where you have probabilities. All futures are possible, but they are not all equally probable. So you need to have something like an algebra where you can do those calculations with uncertainty. By the way, that's one of my big criticisms of Excel, is that with Excel, you're stuck. It's exceedingly difficult to represent uncertainty into a spreadsheet. It doesn't matter if it's Excel or any more modern cloud-based flavor. It doesn't, in a spreadsheet, it's very, very, very difficult to represent that because you have no counterparts. You need to have something that is better than numbers. And here, in this small snippet, I'm illustrating the algebra of random variables that is basically a native feature of Envision. So line 1, what I'm doing is that I'm just generating a Poisson distribution that is discrete from of mean. So 2 is the mean, and I put that in the variable x. Then then I'm doing the same, another Poisson distribution, y, and then I am doing z as the multiplication of x times y. So first, this sort of operation, a multiplication of random variables, may feel very, very bizarre. Why do you even need this sort of things from a supply chain perspective? Let me give you an example. Let's say, for example, that you are in the automotive, aftermarket, and you're selling pad brakes. People don't buy pad brakes by the unit. They either buy 2 or they buy 4. So the question is, if you want to do a forecast, you want maybe to do a forecast that is going to be the probabilities that there are clients that are going to show up to actually buy a certain type of pad brakes. That's going to be, your first random variable that gives you the probability of observing, 0 unit of demand, 1 unit of demand, 2, 3, 4 extra for the pad brakes. And then you will have another probability distribution that is, are people going to take, 2 or 4? And so maybe that's going to be 50-50. Maybe it's going to be, 10% want 2, 90% takes 4. It depends. But the thing is that you have those 2 angles. And if you want to know the actual consumption, the total consumption of pad brakes, you want to multiply, the probability of having a client showing up for demanding this pad brake, and then the probability distribution of buying either 2 or 4. And thus, you need to have this multiplication of those 2 quantities that are uncertain. And obviously here, I'm bypassing that. The 2 random variables are assumed to be independent. And by the way, this multiplication of random variables is known in mathematics. It's basically a Dirichlet convolution, technically. And you can see that I've actually printed on this screenshot the dashboard that end up generated by Envision. So here, the first 3 lines, I'm doing this random algebra calculation. And then the line 4, 5, and 6, I'm just putting those things on display in the web page, in the dashboard that is going to be generated by this script. And you see, I'm just plotting And A1, B2, for example, is just from just think in terms of Excel grids. So basically, the Lokad dashboards are organized just like an Excel grids with positions. So you have like the columns are A, B, C, etc. The lines are 1, 2, 3, 4, 5. And here I'm just putting on display those things in the grid with the colors. And what you can see is that the Dirichlet convolution, so Z, has this very bizarre, super spiky patterns that are actually, by the way, very commonly found in supply chains when people can buy packs or lots or multiples. You frequently end up observing that. And in this sort of situation, usually it's better to decompose the source of the multiplicative events associated to the lot or the pack. And again, you need to have like a programming language that has those sort of capabilities available, at your fingertips. It has to be first-class citizens, and that's exactly what probabilistic programming is about. And that's the way we implemented that in Envision. Okay, differentiable programming. Oof. So this one, I'm just putting a caveat. I'm very, very sorry. I don't expect the audience to really understand what is going on here, and I apologize for that. It's not that your intelligence is lacking. It's just that this topic deserves a whole series of lectures. And by the way, if you look at the plan for the upcoming lectures, there is literally a whole series of lectures dedicated to differentiable programming. So I'm going to go super fast. It's going to be fairly cryptic. I apologize in advance. Let's proceed. So the supply chain problem of interest here is, let's pick a tough problem, like cannibalization and substitution. Those problems are very interesting, cannibalization and substitution. And it's probably one of those problems where basically time series forecasting, which are ubiquitous, fail in the most brutal way. Why? Because frequently we have clients or prospects that comes to me, at Lokad, and they say, Lokad, can you do, 13 weeks ahead forecast for, let's say, those backpacks, for example? And I would say, yes, we can, but obviously, if we take one backpack and we want to forecast the demand for this product, it massively depends on what you're doing with your other backpacks. Because if you have just one backpack, then maybe you're going to concentrate, you're selling sporting goods, you're going to concentrate all the demand for backpacks on this one product. If you introduce 10 different variants, obviously, there will be tons of cannibalization. You're not going to, if you introduce 10 more backpacks, you're not going to multiply the total amount of sales by a factor of 10 just because you've multiplied the number of references by 10. So obviously, you have cannibalization and substitution that are taking place. Those phenomena are prevalent in supply chains. How do you analyze cannibalization or substitution? Well, the way we are doing it at Lokad, I don't pretend that it's the only way, but it's certainly a way that works, is typically by looking at the graph that connects clients and products. Why is that? Because actually, cannibalization happens because actually products are in competition between themselves for the same clients. You see, cannibalization is literally the reflection that you have a client that works with a need, but he has preference and is going to choose one product among the set of products that are, fitting his own affinity and pick only one. That's the essence of cannibalization. And if you want to analyze that, you need to analyze not the time series of the sales, because you don't capture this information in the first place. You want to analyze the graph that connects, the historical graph of transaction that connects clients and products. And it turned out that in most businesses, this data is readily available. For e-commerce, that's a given. Every unit that you sell, you know the client. In B2B, this is the same thing. For B2B, basically, when you're selling something, you know your client. And even in B2C, in retail, most of the time, most retail chains nowadays have loyalty programs where they have like a double-digit percentages of the clients that show up their cards. And so you know who is buying what not for 100% of the traffic, but you don't need that. You just need at least to have like a double digit. If you have like 10% and above, you know, of your historical transactions where you know the pair of clients and products, it's good enough. You can do this sort of analysis. So here in this relatively small snippet, I'm going to detail. I am doing, by the way, an affinity analysis between clients and products, and that's literally the foundational step that you need to take to basically do any kind of cannibalization analysis. And let's have a look at what is happening in this code. So from line 1 to 5, this is very mundane. I'm just reading a flat file that contains a history of transactions. So I'm just reading, you know, transaction.csv. It's just a flat file, and basically I have a flat file that has 4 columns, which are dates, product, client, quantity, you know, something very, very basic. I'm not even using all those columns, but just to make the example a bit more concrete. So I'm just like a transaction history. I assume that on this set of transactions, both the client that the clients are known, basically, for all those transactions. So super mundane, I'm just reading there. Then then line 7 and 8, I'm merely creating the table for products and the table for clients. In a real production setup, I would typically not create those tables. I would read those tables from, you know, other flat files elsewhere. So I would not, you know, create them. But here I wanted to keep the example super simple. So I am just, you know, extracting a product table just from the products that I observed in the transaction history. And I do the same for clients. So you see, it's just like a trick to keep it like super simple. Now line 10, 11, and 12, latent spaces. Okay, so this is going to become a bit more obscure. So first line 10, I am just creating a table with 64 lines. The table doesn't contain anything. It is only defined by the very fact that it has 64 lines, and this is it. So this is like a placeholder, nothing. So the only thing that matters is 64 lines, and this is it. So it's like a trivial table, many lines, no columns. It's not so useful, just like that. Then P is basically it's a Cartesian product. It's a mathematical operation. It's all the pairs. So it's literally a table where you have one line for every line in products and every line in the table L. So it's Cartesian products. So basically, this table P has 64 more lines than the products table. And I'm just doing the same thing for clients. So I'm just inflating those tables through this an extra dimension that is this table L, and that's going to be my support for my latent spaces, which is exactly what I'm going to learn. And if I want to understand what I want to learn is for every product a latent space, which is going to be a vector of 64 values, and for every client a latent space of 64 values as well. And if I want to know the affinity between a client and a product, I just want to be able to do the dot product between the two. The dot product is just like the pointwise multiplication of all the terms of those two vectors, and then you do the sum. It may sound very technical, but literally it's pointwise multiplication plus sum. That's just a dot product. And those latent spaces, it's just, you know, fancy jargon to say I am just creating, you know, a space with parameters that are a bit made up where I just want to learn. And and literally all the differentiable programming magic happens in literally in literally 5 lines, which is from 14 to 18. So I just have one keyword, autodiff, and transaction. So that says that this is a table of interest. That's a table of observation. So I'm going to process this table line by line to do my learning process. Here I am in this block. I am declaring a set of parameters. The parameters are the thing you want to learn. Think of them as numbers, but you just don't know yet the value. So those things are just going to be initialized randomly. You know, it's random numbers. And so I introduce x star. I'm not going to delve into y x star exactly what it's doing. maybe in the questions, and then y. So I'm just introducing a list of parameters, and then I am returning an expression that is my loss function, and that the sum. And by the way, the idea of collaborative filtering or matrix decomposition is just that you want to learn latent spaces that fits all your edges in your bipartite graph. I know it's a bit technical, but what we are doing is literally very simple supply chain wise. We are learning the affinity between products and clients. And I know that it seems probably like super opaque, but stay with me, and there will be more lectures where I give you, a more thoughtful, introduction to that. But the whole thing is done in 5 lines, and that's completely remarkable. And when I say 5 lines, I am not cheating by saying, look, it's only 5 lines, but I am actually making a call to a third-party library of gigantic complexity where I'm burying all the intelligence. No. Here, in this example, there is literally no machine learning magic beside the 2 keywords are autodiff and params. Autodiff to define a block where differentiable programming will take place. And by the way, this is a block where I can program anything. So literally, I can inject our program. And then I have params to declare my params, and this is it. So you see, there is no opaque magic, going on. There is no there is not 1 million line libraries in the background that is doing all the work for you. No, everything that you need to know is literally in this screen, and that's the difference between a programming paradigm and a library. It's literally the programming paradigms just give you access to seemingly incredibly sophisticated capabilities, such as doing cannibalization analysis, with literally a few lines of code without resorting to massive third-party libraries that just wrap the complexity. It's literally, it transcends the problem to make it way simpler to the sense that you can have something that seems super complicated that is solved in just a few lines. So the way it works, by the way, a few words on how differentiable programming works. There are 2 insights. One is automatic differentiation. At school, for those of you who had the luxury of having maybe some engineering training, you've seen 2 ways to compute derivatives. There is a symbolic derivative. So if you have x squared, you do the derivative by x, and it gives you 2x. That's a symbolic derivative, and then you have the numerical derivative. So basically, if you have a function f of x that you want to derivate, it's going to be basically f prime of x is roughly equal to f of x plus epsilon minus f of x divided by epsilon. That's the numeric derivation. Both are actually not suitable. The symbolic, for what we are trying to do here, the symbolic derivation has problems of complexity. When you do a symbolic derivation, your derivative might be a program that is much more complex than the original program. So that's a big problem. And the numerical derivation is numerically unstable. So you will have plenty of dumb problems of numerical stabilities. Automatic differentiation is a completely fantastic idea that is dating from the 70s and that has been rediscovered by the world at large in the last decade. And it's the idea that you can compute the derivative of a program, of an arbitrary computer program. And when you think about it, it's kind of mind-blowing. And even more mind-blowing, if you have a program, you can compute the derivative of the program. And when you do it through automatic differentiation, the program that is the derivative have the same compute complexity than the original program, which is stunning. So literally, differentiable programming is just a combination of automatic differentiation. And then in this program, you will have parameters that you want to learn. And how do you learn then? When you have the derivation, it means that you can bubble up a gradient. And with stochastic gradient descent, you can bring small adjustments to the value of the parameters so that by touching those parameters, you will incrementally, through many iterations of the stochastic gradient descent, converge to parameters that make sense and that do what you want the thing to be learned or done or optimized. Differentiable programming can be used both for learning problems, just like the one I'm illustrating. So I want to learn the affinity between my clients and my products. but it can also be used to do numerical optimization problems, such as optimizing things under constraints, etc., etc. It's very scalable as a paradigm, and as you can see, this thing has been made, a first-class citizen in Envision. By the way, there are still a few things that are, I would say, in progress in terms of Envision syntax. So don't expect exactly those things yet. We are still touching a few things, but the essence is there. I'm not going to discuss, the fine prints of the tiny few things that are still moving. Now, versioning code and data. So let's move to another problem, and that is relevant for the production gradiness of your setup. So the problems that you face typically in supply chain optimizations are Heisenbergs. So what is a Heisenberg? That's a sort of super frustrating kind of bug. You have an optimization that takes place and that gives you garbage results. That you had a batch that do calculation for inventory replenishment during the night, and the morning you just discovered that some of those results were nonsense and you did costly mistakes. It's unfortunate, and so you don't want the problem to ever happen again. You want to fix it. So you rerun your process, and when you rerun your process, the problem is gone. So you had a problem that generated garbage replenishment during the nights, and you rerun the thing, and you can't reproduce the problem. The problem do not manifest itself. That's a Heisenberg. And I would say it may sound like a weird edge case, but in the first few years of Lokad, we were facing those problems over and over and over. And I've seen a lot of supply chain initiatives, especially of the data science kind, that died just due to the fact that their Heisenbergs were never solved. So basically, they had bugs that were happening in production. They were trying to reproduce the things locally. It wasn't reproducing, so the things were never fixed. And that after a couple of months of super, I would say, of panic mode, the whole thing was typically, usually, quietly shut down, and people were back to their Excel spreadsheets. So the idea is, if you want to have complete replicability of your logic, you need to version the code. And so most people here in the audience who are maybe software engineers or maybe data scientists may be familiar with the idea of versioning the code. But you also want to version the data, all the data, so that when you have your program that executes, you know exactly which version of the code and exactly which version of the data, so that if the next day you want, because why can't you can't replicate the problems the next day? Because 12 hours down the road, when you try to rerun your program, the things that has most likely happened is that the data has changed because there is new transactions, there is a new product file, there is this or that or that. So basically, the problem does not manifest itself because the data has changed, and so the conditions that were triggering the bug in the first place are not present anymore. So you want to make sure that your environment, your programming environment, whenever you face a problem, you can exactly replicate the logic as it was in production at this specific point of time and the data as it was at this very specific point of time. And so here, this is literally having a complete versioning of everything. And by the way, again, the programming language and the programming stack have to cooperate to make that possible. It is possible to achieve this sort of results without resorting to the programming paradigm being part of a first-class citizen of your stack, but then it means that the supply chain scientists must be exceedingly careful about all the things that they do, all the things, the way they program. Otherwise, they won't be able to replicate. But that's putting an immense pressure on the shoulder of your supply chain scientists, which are already under immense, supply chain pressure. You don't want those people to have, in addition, to just deal with completely accidental complexities, such as the fact that they can't even replicate their own results. So you want to have a bit, what we colloquially call at Lokad, a time machine where you can replicate everything at any point in the past. And beware, it's not just what happened last night. Sometimes you discover a mistake that you've done, but you discover that long after the fact. Just for example, if you pass a purchase order to a supplier that has a 3-month lead time, you may discover, 3 months down the road that this purchase order was nonsense. And now you need to go back 3 months in the past to go back at the point of time where you actually generated this bogus purchase order to figure out what was the problem. So it's not about just versioning the last hours of work. It's literally the last year of execution where you want to have a complete history. Okay, yet another one, secure programming. Ransomware are on the rise. I know at Lokad that literally we have a couple of clients, more than a couple of clients that are literally fighting for their survival against ransomwares. I mean, IT attacks, cyber attacks are no jokes for supply chains. It's massively disruptive. I mean, it costs a lot of money. And so you really need to ask yourself, when I am doing something software-driven, am I actually making the situation worse for my company? Am I making my company, my supply chain, even more vulnerable to cyber attacks and cyber risk in general? And here, I would say Excel is, from this perspective, Excel is not too great, and neither is Python. You see, those components, they are programmable. And so the problem that you can have plenty of problems that are carried through those programs. So for example, whenever you have somebody, you have a team that can, write Python programs, they can, in the very programs themselves, you can have tons of security vulnerabilities. And remember, if you have a team of data scientists, of supply chain scientists who are dealing with supply chain problems, they can't afford to do what is regularly done in I would say, in the software industry, which is have a very, careful, iterative, peer-reviewed process of the code. You can't afford to spend many days reviewing the code, making back and forth of exchanges, etc. If you have like a tariff that has just changed overnight, it needs a response now. Or if you have like a warehouse that just got flooded, you literally have 24 hours to rebalance what remains of your supply chain, to make the most of the assets that you still have. You can't just have a process that is going to take weeks, where you have a ticket, you're going to produce code, specification, reviews, and all of that. It doesn't work. And so the problem is that we have just said that we need to have programming capabilities, but we are giving programming capabilities to people who have, by default, the potential to bring a lot of harm to the company accidentally. I mean, it can be even worse if it's intentional with a rogue employee, which is also a possibility. But even if we put the rogue employee aside, you still have the problem of somebody who did accidentally expose an inner part of the IT systems. And remember, those supply chain optimization systems, by definition, they will have access to tons of data across the entire company, because that's what supply chain optimization is about. You need to access the data, end to end, from the data of your suppliers to the data of your clients. So you are trusted with a lot of data, and thus data is not just an asset, it's a liability as well. So you want a programming, as a programming paradigms, what you want is secure programming. So you want a programming language where there are entire classes of things that you cannot do. For example, why should you have, for supply chain optimization purposes, a programming language that can do system call? So what do I do system call? Obviously, Python can do system call. So it can go back to the operating system and interact with the operating system. Excel can do the same. And the question is, why would you want a programming system, a programmable system that has those capabilities in the first place? That's literally, you're buying the gun to shoot a bullet in your feet. So you want something where you have entire classes of features that are just absent because you don't need them for supply chain optimization. And if they are present, they are a massive liability. And so you're not going to, if you introduce those programming paradigms, those programmable capabilities in your organization, but you don't have the tools that that basically enforce by design secure programming, you're just increasing the risk of cyber attacks, you're increasing the risk of ransomware, you're just making things slightly worse. So I mean, obviously it's always possible to compensate by having, by doubling the size of the team in charge of cybersecurity, but that's very, very costly, and realistically I'm not sure how well this thing will fare when facing the urgency. Again, supply chain is about how do you cope in a way that is completely secure, that is correct by design, when this is a complete urgency and you don't have the time for the usual processes, you don't have the time for the review, the circles of approval, etc., etc. You need to act, and you need to act now, not 3 weeks from now. And then you also want, in terms of secure programming, to eliminate all class of, I would say, very mundane problems, null reference exceptions, out of memory, off by one loops, side effects, etc., etc., etc. There are so many problems that are pure accidental complexity. So, in conclusion, that has been a tough lecture. I hope there is still some people alive in the audience after this lecture. But my conclusion for you is tooling matters. There is this adage which is, don't bring a sword to a gunfight. You need to have the proper tools. You need to have the proper programming paradigms. You can't have the toy paradigms that you just discovered, at university. You need something that is professional, and that will give you, the production gradiness that your supply chain needs to achieve greatness. Again, I'm pretty sure you can do things with toys, but it's just not. It's probably going to be not great. If you have like a fantastic musician is able to do music with just a spoon. But if this person has, a real music instrument, it can be, a notch better. So now let's proceed with the questions. So let me have a look. So by the way, there is a delay of something like 20 seconds. So what you're saying is that there is some bit of latency in the streams between the questions and the video you're seeing and me reading your questions. What about dynamic programming in terms of operation research? That's a question from Ogoskan Osden. So dynamic programming, despite the name, is not a programming paradigm. It's more an algorithmic technique. And this idea is that if I want to summarize in ways that are not completely obscure dynamic programming, it's typically that you realize to solve, to perform an algorithmic task, so solving a certain problems, you are going to repeat yourself very frequently. So you're going to do the same sub-operation over and over and over. And so dynamic programming is actually a specific case of the space-time trade-off that I've just described, in the hardware miscibility, where basically you invest a little more on memory to save time on the compute side. It was one of the earliest algorithmic techniques that was uncovered, I think something like back in the 60s, 70s. It's a good one. I believe that the name is a bit unfortunate because it's there is nothing really dynamic about it, and it's not really about programming. It's more about the conception of algorithms. It is a very good algorithmic techniques, but for me, despite the names, this is not what qualifies as, I hope I understood your questions correctly, but that doesn't qualify it as a programming paradigms. It's more like a specific algorithmic techniques that is of very high interest, but this is fundamentally, a sub-element of the field of algorithms. NR, Johannes, would you kindly provide some reference book that every good supply chain engineer should have? Unfortunately, I'm new to the field, and my current focus is data science and system engineering. Frankly, I don't know. Again, I've very, very mitigated opinions about the existing literature. That was literally my first lecture. I presented 2 books. So first, I gave 2 books that I believe to be the pinnacle of academic studies as far as supply chain is concerned, in my first lecture. So if you want to read 2 books, you can read those books. Yet I have, I would say, a constant problems with the books that I've read so far. Basically, you have people who are basically where it's collection of toy numerical recipes for idealized supply chain. And I believe that those things, they just don't approach the problem, the supply chain from the right angle, and they completely miss the point that it's a wicked problem. So literally, yes, you have like entire catalogs that are very technical with equations, algorithms, you have a lot of things, theorem, proof, and all of that, I believe, is entirely missing the point. And that's why you have an extensive body of literature and it's not used. And then you have another style of I would say, more like consultant style of about supply chain management. You have tons of those books. You can very easily recognize those books because they do sports analogy every 2 pages. So every 2 pages you have some kind of sport analogy that will tell you that it's like a book that has been written by a consultant. And then they have all sorts of I would say simplistic diagrams, 2 by 2, which are variants of the SWOT, strength, weakness, opportunity, threats, diagrams, the sort of I would say business school nonsense or actually very low quality way of reasoning. So the problem is that those books tend to be better on understanding that supply chain is a wicked undertaking. So they understand, much better the essence that it's a game played by people where all sorts of super bizarre things can happen and you can be smart in tons of ways. I give them credit for that. The problem of all those books that I would say that are, I would say, written by typically consultants or professors of management school. My problem with those books is that they are not very actionable. I mean, literally the message boils down to be a better leader, be smarter, have more energy, and for me, this is completely the sort of self-help that is not actionable. Doesn't give you, this is not science, that doesn't give you elements that you can turn into gold in ways that are uber accretive, that are uber capitalistic. Like software can. So sorry, go back to the first lecture, read the 2 books if you want, but I'm not sure that it will be time super well employed. I think, it's good to know what people have written. And if you want, on I would say the consultant side of the literature, probably my favorites in terms of books would be the work of Gattorna that I have not listed in the first lecture. So again, all is not bad. Some people have a lot more talent, even if they are more like consultant-ish, and so you can check the work of Gattorna. I will be listing that in the. He has a book on dynamic supply chains. I will be listing the book in the references. So Fro XX1203. Welcome back. How do you use parallelization when dealing with cannibalization or assortment decisions where the problem is not easily parallelized? Why is it not easily parallelized? Stochastic gradient descent is fairly trivial to parallelize. There is, you see, it's literally when you it's literally something where, in terms of compute, you do stochastic gradient steps that are taken in random orders, and you can literally have multiple steps at the same time. So yes, I mean, I believe anything that is driven by stochastic gradient descent is actually fairly trivial to parallelize. So I'm not too sure about that when dealing with cannibalization. So what is more difficult is to deal with another sort of parallelization, which is what comes first. If I put this product first, then I make a forecast, but then I take another product, it modifies the landscape, and so the answer is you want to have a way where you can address, the whole landscape frontally. You don't say, first I introduce this product, then I do the forecast, then I introduce another product, and then I redo the forecast, remodify the first one. No, you don't do that, you just do it frontally. all those things at once at the same time. Again, you need more programming paradigms. The programming paradigms that I've introduced today can go a long way for that, but literally when it comes to assortment decisions, this sort of problems, they don't present, any great difficulties for parallelization. Same thing if you have like a whole retail network and you want to optimize the assortment of all your stores. Literally, you can have computations that happens for all the stores. Obviously, you don't want to do the thing in sequence where you optimize the assortment for one store, and then you say this is it, and you do the second store. That's the wrong way to do it. But you can, in parallel, do around, optimize a bit the whole network, propagate all the information, and then repeat. I mean, there are all sorts of techniques, and again, the tooling can greatly help you to do that in ways that are much easier. Richard Lubienski, are you using a graph database approach? No. No. But, or actually not in the canonical sense. There are many graph databases on the market that have of great interest. What we are using internally is at Lokad, we have literally eliminated all the layers from the persistence to the very top, I would say to the very top of the front end of the compiler for the language itself. You see, most of the problem lies in terms of performance in modern computer systems, in the fact that you have many layered systems. So for example, if you have a graph database, it means that you will have at least a subsystem that is a graph database, and the calculations will, and the data will be going back and forth in and out the graph database all the time. And no matter how you take the problems, this boundary between the graph database and the rest of your systems will introduce a lot of friction. You will spend a lot of time just moving the data around, getting the data out of the graph database, getting the data in the graph database. So the way Lokad is doing it is we have an approach with complete vertical integration through a unified monolithic compiler stack to remove entirely all those traditional elements that you would find in a classical stack. And that's how we achieve typically, I believe, very good performance instead of compute performance, very close to the metal, not because we are fantastically smart coders, but just because we have eliminated pretty much all the layers that traditionally exist in the systems. So that, I hope that answers. So Lokad is using literally no database at all. We literally have the compiler that takes care of everything down to the organization of the data structures for persistence. It's a bit weird, but it's much more efficient to do it that way. And this way, you play much more nicely with the fact that you compile a script toward a fleet of machines on a cloud. This is your target platform in terms of hardware. It's not one machine, it's a fleet of machines. Ugo Khan Osden, what is your opinion on Power BI, which also run Python codes and related algorithms like gradient descent, greedy, etc.? Okay, so the problem is that the problem that I have with anything business intelligence in general, Power BI being one of them, is that this is a paradigm where that I think is inadequate for supply chain, where you see all problems as an hypercube where you have dimension that all that you do is slice and dice. So you see at the core you have a problem of expressivity which is very limiting. And by the way, that's so you end up with a paradigm where at the core of your design, you have this hypercube, and it is exceedingly limiting. And thus, what you do if you end up having Power BI and that you put Python in the middle of it, is why do you need Python? Well, you need Python because you have this expressiveness that is related to the hypercube that is super poor. So how do you regain expressiveness? You have your hypercube that is way too poor in terms of programmable expressiveness. So you add Python in the middle. But then remember what I just said for the previous question about those layers. The curse of modern enterprise software is you have too many layers. Every single layer that you add is going to add, problems in terms of inefficiencies, in terms of bugs. If you use Power BI plus Python, actually you're going to have like way many layers. So you have Power BI that sits on top of other systems. So you have already multiple systems, before Power BI. Then you have Power BI on top, and then on top of Power BI you have Python. But is Python acting on its own? No. Chances are that you're going to use, libraries of Python, pandas or NumPy or stuff. So you have layers in Python that are going to pile up. And so you end up with dozens of layers. And you can have bugs in any of those layers. So the situation is going to be quite nightmarish. So I'm absolutely, not a believer of those solutions where you just end up having a massive number of stacks where, there is this whole joke where how you can solve in C++, you can always solve any problem by adding one more layer of indirection, including the problem of having too many layers of indirection. You see that obviously this is a bit nonsensical as a statement, but what I'm saying is that I profoundly disagree with the sort of approach where people had a product where the core design was inadequate, and instead of tackling frontally the problem that the hypercube that is at the core of that is at the core of the Power BI design, you end up by putting stuff on top while your foundations are shaky. This is not the way to do. And you're going to have, I would say, poor productivity, ongoing battles with bugs that you're never going to solve. And then in terms of maintainability, it's just a recipe for something that is a nightmare. Pierre Garcia, welcome back too. And how can the results of a collaborative filtering analysis be plugged in the demand prediction algorithm for each products, backpacks, for example? Oh, that's, sorry. Next lecture. I'm pulling the card Joker. That is literally the sort of topic that we'll have in next lectures. Yes, it's not. I'm not finished, but this is the foundation. This is the hard part, and the idea is that you don't. The short answer. You don't want to plug that into an existing prediction algorithm. You want to have something that is much more natively integrated. That's not like you do that and then you go back to your old ways of doing forecasting and then you're done. No. You just discard the old way of doing the forecast and you just do something that is radically different, that is just one step beyond, and that leverage that. But I will keep that into a later lecture. I'm sorry, it would be way too much for today. I'm sorry. I'm calling the Joker. Well, I guess this is it. This was quite a lecture today. Thank you very much, everyone, for attending this lecture. The next lecture will be, I believe, something like Wednesday, January 6th. So it will be same time, same day of the week, but I will be taking some Christmas vacations. So I wish everyone a happy Christmas and a happy New Year, and then we will continue our series of lectures next year. Thank you very much.